is hc divided by lambda. The c cancels, the lambdas cancel, and you see that our delta t multiplied by delta E is approximately equal to h Planck's constant. Now, a slightly more tedious and careful calculation will give us the following equation. We're not going to provide this equation in this lecture. We're simply going to state it. So, delta t multiplied by delta E is approximately equal to h Planck's constant divided by 2 pi, where h divided by 2 pi is given by h bar. So, this is the equation for the uncertainty of our energy and time. So, basically, this equation gives us the uncertainty in energy transferred to an electron over a time interval given by delta t. So, we see that the smaller the quantity of time is, the smaller the interval of time is, the greater the uncertainty in energy is. So, in the next several lectures, we're going to look at several examples that deal with both forms of Heisenberg's uncertainty principle. In this example that deals with Heisenberg's uncertainty principle, we're going to compare the uncertainty in position of a macroscopic object and a microscopic object. So, let's begin. An electron and a tennis ball are traveling along the x-axis in the positive direction with a constant velocity of 50 meters per second. Now, if the mass of the tennis ball is 58 grams and the velocity is measured to a precision of 0.02%, then we want to find the uncertainties in position of each one of our two objects. That is, we want to compare those two uncertainties. So, let's begin with the tennis ball. What exactly is the uncertainty of position along the x-axis of our tennis ball that is traveling with a constant velocity of 50 meters per second and which is measured to a precision of 0.02%. So basically, using the information and by applying Heisenberg's uncertainty principle, we can calculate what this uncertainty in position is. So based on Heisenberg's uncertainty principle, the product of the uncertainty in position and the uncertainty in our momentum is approximately equal to h bar, our constant, 1.055 times 10 to negative 34 joules multiplied by second. So basically, using the given information, we can calculate what delta p is. So if we know what delta p is and h bar, we can calculate what delta x is. So we solve for delta x by rearranging this equation. So delta x is approximately equal to the ratio h bar, our constant, divided by delta p, the change or uncertainty in our momentum. Now, how exactly do we calculate the uncertainty in our momentum given this information? So, recall that change in momentum is equal to the product of the mass of the object and the change in velocity. So, change in p is equal to m multiplied by change in v. Now, what exactly is the meaning of change in v? Change in v is simply the uncertainty of our velocity, and we can get that by taking 50 meters per second and multiplying by 0.002. So, 0.0002 multiplied by 50 meters per second multiplied by the mass in kilograms gives us the uncertainty in our momentum. So, we take our constant and divide it by this, and we get about 1.82 times 10 to the negative 31 meters. Next, let's move on to our electron. So the electron is traveling in the positive direction along the x-axis with a velocity of 50 meters per second that is measured to a precision of 0.02%. So once again, we basically apply this same equation, we rearrange and solve for delta x, the uncertainty in our position along the x-axis, now of the electron. So basically, we follow the same exact steps, but instead of using a mass of 58 grams, we use a mass of 9.11 times 10 to negative 31 kilograms, the mass of our electron. So we plug in our values, and we see that delta x, the uncertainty in our position along the x-axis of the electron, is 1.16 times 10 to the negative 2 meters. So notice, where this quantity is very, very, very small, this quantity is much greater and much more noticeable. So what exactly is the meaning behind that? So, as it turns out, whenever we're dealing with objects that are on the macroscopic level, the uncertainties involved in things like position for objects on the macroscopic level are so small that we usually can neglect them, as in this case. The uncertainty is so small that for objects that are macroscopic, we basically neglect Heisenberg's uncertainty principle. But when we deal with objects on the atomic and subatomic level, the uncertainties become much greater, so we can no longer neglect them. As we briefly discussed in the lecture on Introduction to Quantum Mechanics, we said that quantum mechanics does not take the same approach in studying the behavior of microscopic and macroscopic objects. So in this lecture, we're going to discuss the statistical approach that is taken by quantum mechanics as well as the deterministic approach that is taken by classical physics. So classical physics takes on an approach known as the deterministic approach in studying the behavior of the motion of macroscopic as well as microscopic objects. It basically treats objects as if they were simple particles. So according to the deterministic theory, if we know a certain set of given quantities, such as velocity and position, and if we know all the forces involved that act on that object, we can readily determine the future position of that object. We can determine the pathway that our object takes. For example, in classical physics, if we let an object fall from a height of 10 meters from the bottom, from the surface of the Earth at a known initial time of, let's say, t equals 0 seconds, and we neglect a resistance, we know the only force acting on an object is the force of gravity. So if we know the force is acting on the object, if we know the initial position as well as the initial velocity of that object, even if it's a macroscopic or microscopic object, we can determine the future pathway that our object will take. We can also determine the exact position and velocity of the object at any later time. So this is the approach that classical physics takes, and it is known as the deterministic approach. So quantum mechanics, however, takes a completely different approach on studying the behavior of macroscopic and microscopic objects. As we already saw in our discussion on the double slit experiment using electrons, there is absolutely no way in actually knowing the pathway that any one electron will take, nor is it possible to know exactly where that electron will end up. In fact, Heisenberg's uncertainty principle tells us that it is impossible to know precisely the position as well as the velocity, the momentum of any electron at any given moment in time. So instead of using the deterministic theory, the deterministic approach that classical physics uses, quantum mechanics uses a different theory known as the statistical theory. So even though we cannot know with exact certainty where any one electron will actually end up, we can describe the future position and velocity of an electron using probability. And this interpretation of macroscopic and microscopic objects is known as Copenhagen's interpretation. So basically it states that there is an inherent uncertainty in being able to predict the pathways and quantities that describe the motion of any object, being a microscopic object or a macroscopic object. Now this uncertainty comes from the fact that ordinary objects do not simply behave as particles, but they can also behave as waves. According to quantum mechanics, since electrons are not simple particles, since they can also act as waves, they cannot follow any simple pathway that is predicted by the deterministic approach that classical physics takes. So basically, classical physics uses an approach known as a deterministic approach. So basically, classical physics assumes that all objects, being macroscopic or microscopic, are exact particles, are simple particles. So that basically means if we know a certain set of quantities, initial quantities, as well as all the forces involved that act on that object, we can readily predict the future location and pathway of that object. On the other hand, quantum mechanics takes a statistical approach to studying the behavior of microscopic and macroscopic objects. Basically, it states that there exists an uncertainty in nature that comes from the wave-particle duality of matter. Matter does not always act as simple particles, but it can also act as waves, and as a result, there exists an uncertainty in being able to predict the pathway of any object, such as an electron. So finally, in this lecture, we're going to discuss the famous and important Schrödinger equation of quantum mechanics. Now, what exactly is this equation? Where does it actually come from? And what important information does this equation provide us with? These are some of the questions we're going to discuss in this lecture. So let's begin by calling a very important principle in quantum mechanics. So quantum mechanics basically incorporates the wave-particle duality of matter. That is, a system can act as a wave or it can act as a particle. Now, in quantum mechanics, we describe any system such as an electron by using a quantity known as the wave function. Now, when we treat our system such as our electron as a wave, in that case, the wave function represents the displacement or amplitude of the wave produced by that electron. On the other hand, if we treat our system, once again, for example, our electron as a particle, then in this case, the wave function allows us to calculate the probability of finding that particle, that electron, at some moment in time and some location in space. More specifically, to calculate the probability, we take the square of the absolute value of the wave function, which is, by the way, given by the Greek letter psi. Now, what exactly does this tell us? Well, basically, in order to be able to describe any system such as our electron in quantum mechanics, we must be able to determine the wave function energy, and that's exactly where the Schrödinger equation actually comes into play. The Schrödinger equation is basically a differential equation that we use to solve for the wave function quantitatively. So basically, the wave function is a solution to the Schrödinger equation, which itself is a differential equation. Now, the question is, where exactly does the Schrödinger equation actually come from? Can we actually derive the Schrödinger equation from some underlying principle? Well, in the same way that Sir Isaac Newton invented the second law of motion, so basically, Isaac Newton invented F equals m times a to describe what happens to an object when an force acts on it, and then that equation was basically confirmed experimentally. The Schrödinger equation was also invented and was tested and confirmed experimentally. So this means that there is no way to actually derive the Schrödinger equation in the same exact way. There's no way to actually derive the equation F equals m times a. These equations are basically equations that can be readily confirmed experimentally and cannot actually be derived in any way. Now, the question still remains, what does the Schrödinger equation actually look like? What form does this equation take? So basically, in order to determine the form that the equation takes, we will use the conservation of energy. So that's the idea that we're going to use to determine what the Schrödinger equation is. Now, in this particular lecture, we will also assume that the wave function that we are dealing with does not actually depend on time, and the wave function only depends on the spatial position of our system lying along the x-axis. So psi, the wave function, only depends on x and is independent of the time. So that basically means, since the Schrödinger equation has a solution that is equal to the wave function, and the wave function is time independent, that means the Schrödinger equation that we're going to determine in this lecture is also time independent. Now, a second form, a more complicated form of the Schrödinger equation that we're going to address in a future lecture is the time-dependent Schrödinger equation. So, in this lecture, we're only going to focus on the time-independent Schrödinger equation. So, let's begin our determination of this equation by looking at the following diagram. Let's suppose that a particle is moving along the x-axis, and no forces are actually acting on that particle. So that means our particle is in fact a free particle. So, for example, we have an electron that is moving along the x-axis in a positive direction. No forces act on that particle, so that means that the energy of our particle is constant, and that implies that the momentum of that particle is also constant. Now, we know that Louis de Broglie basically told us that our momentum p of our particle is equal to h divided by lambda. Now, if we take our equation and solve for lambda, the wavelength of the wave produced by the particle, that is equal to h divided by p. So we see that since h is a constant and p is also a constant because no forces are assumed to act on the particle, then for this particular case, the wavelength is also constant. So, let's begin with step 1. So, to basically describe the wave produced by a particle, such as this electron moving along the x-axis, we might expect that the wave function satisfies a differential equation that is similar to the classical equation of our wave. That is given by the following formula. So our wave function psi with respect to x and t, our position and time, is equal to a constant multiplied by sine of kx minus omega t plus b, another constant multiplied by cosine of kx minus omega multiplied by t. Once again, this is the classical wave equation for mechanical and electromagnetic waves. Now, since we are assuming that our time is independent, that is, the Schrödinger equation is independent of time and only depends on the spatial position x along the x-axis, we can set t equal to 0. Then this disappears, and this also disappears. So we see that psi, our wave function, with respect to x is equal to a sine kx plus b cosine kx. Let's label this equation as equation 1. So, what exactly is the importance of equation 1? What does it actually give us? Well, this equation gives us the equation of the wave function for a free particle, a particle that does not actually feel any force. And this equation is important because it gives us the solution to the Schrödinger equation. So, basically, whatever the time-independent Schrödinger equation actually looks like, that equation has to have a solution that satisfies equation 1. And that is the importance of this equation. Now, what exactly is k? Well, k is a constant, and it's equal to 2 pi divided by lambda. We know that from classical physics. Now, lambda from this equation is h divided by p. So we go from this equation to this equation by replacing lambda with h divided by p. Now, we can take the 2 pi and bring it to the bottom, and we see that k is equal to p divided by h divided by 2 pi. So this denominator is equal to h bar, where h bar is a constant and is equal to 1.055 times 10 to negative 34 joules multiplied by seconds. Now, so k is equal to p divided by h bar, so k is a constant, and k is given by these two quantities. So, now let's move on to step 2. So in step 2, we're still looking at this diagram. So now let's suppose we want to apply the conservation of energy. So since this particle is moving along the x-axis in the positive direction with a velocity that is constant given by v and a mass m, then the total energy of our particle, our system, E, is equal to the sum of the kinetic energy of the particle and the potential energy. So E is equal to k plus u. Now, in this lecture, we're going to focus on non-relativistic kinetic energy. So that means the non-relativistic kinetic energy k is equal to 1/2 m times v squared. Now, what exactly is v? Well, recall that our momentum p is equal to m times v, and that implies that our v is equal to p divided by m. So we can replace our v with p divided by m, and we get this result. So E, the total energy of our particle, is equal to p squared divided by 2m plus u, the potential energy, where this is our non-relativistic kinetic energy. Now, from this equation, we know that k is equal to p divided by h bar. Now, we can rearrange this equation, and we see that p is equal to k multiplied by h bar. So now we replace our p with k multiplied by h bar, and this gives us equation 2. So we label this as equation 2. So we saw in step 1 that equation 1 gives us the general form of the solution, the wave function, which is the solution of the Schrödinger equation. And in step 2, what this equation actually tells us is, it tells us that whatever the time-independent Schrödinger equation actually looks like, it has to satisfy, it has to look like equation 2. So once again, we conclude the following important points. Whatever the Schrödinger equation looks like, it must satisfy equation 2, which comes from the conservation of energy, and the solution of this Schrödinger equation must take the form of equation 1. Now, in the next part of this lecture, we're actually going to use these two facts to determine what the time-independent Schrödinger equation actually looks like. So let us now continue from where we just left off. So in section 1 and section 2, we saw that we are trying to find a one-dimensional time-independent differential equation known as the Schrödinger equation that looks like equation 2, and which has a solution known as the wave function that has the form of equation 1. So if we are to determine a differential equation, we actually need a differential equation to work with. So let's take equation 1, and let's take the second derivative of equation 1 with respect to x. So the second derivative of our sine with respect to x is equal to negative k squared, a constant, multiplied by a sine kx plus b cosine kx, where a and b are constants. K is equal to p divided by our h bar, and x is simply our position of our particle along our x-axis. So because we're only examining one dimension, one axis, this equation is in fact a one-dimensional differential equation. Now, let's look at the following inner portion. So a sine kx plus b cosine kx is simply equation 1, and it's equal to psi with respect to x. So this inner portion is simply equal to psi with respect to x, our wave function. So this is equal to the following equation. So d2, so basically our derivative, second derivative of the wave function with respect to x is equal to negative k squared multiplied by psi with respect to x. So let's call this equation 3. So notice equation 3 is in fact a differential equation. So that means we're one step closer to determining what the one-dimensional time-independent Schrödinger equation is. So the next goal is to basically take equation 2 and make equation 2 look like equation 3. So notice that both equation 2 and equation 3 have something in common. They have the k squared term in common, which appears on the right side of equation 3, and which appears on the right side, the first term of equation 2. So let's take equation 3 and multiply both sides of equation 3 by the term negative h bar divided by 2 2m. Remember, we're trying to make equation 2 look like equation 3. So if we multiply both sides by a and h bar divided by 2m, which is basically this fraction here, we get the following result. So a and h bar divided by 2m multiplied by the second derivative of the wave function with respect to x is equal to a squared multiplied by k squared divided by 2m multiplied by the wave function with respect to x. Finally, let's take equation 2 and multiply the left and the right side of equation 2 by our wave function with respect to x. So the left side becomes e multiplied by psi with respect to x is equal to, this quantity becomes k squared, our bar squared divided by 2m multiplied by psi x plus u with respect to x multiplied by our psi with respect to x. So now let's take a closer look at this equation. Notice that the first term that appears on the right side of the following equation is simply this quantity. So we have h bar squared multiplied by k squared divided by 2m multiplied by this, and this entire thing is equal to this quantity. So if we replace this with this, we get the following result. So e multiplied by our psi with respect to x is equal to u, which is also with respect to x, multiplied by psi with respect to x minus h bar divided by 2m multiplied by the second derivative of the wave function with respect to x. So this is exactly the one-dimensional, time-independent Schrodinger equation that we were looking for. Notice that we did not actually derive this equation, but rather we determined this equation, and then to actually confirm and test whether or not this equation actually works, we have to conduct experiments and see whether or not this equation actually fits the experimental result. In this lecture, we're going to try to understand and interpret the meaning behind Schrodinger's equation that is used in quantum mechanics. Now, first, let's recall the difference between classical mechanics and quantum mechanics. In classical mechanics, we study the behavior and motion of an object by using a certain set of laws. So we use Newton's laws of motion as well as the law of conservation of energy to study and describe the behavior of our system. Now, a system could be any object that we are studying, and in this particular lecture, we're going to use the electron as our system. So in classical mechanics, an electron is believed to be a solid sphere. It's believed to be composed entirely of matter, so it acts exactly as a particle. Now, on the other hand, in quantum mechanics, we incorporate the wave-particle duality of nature. That means our electron doesn't only act as a particle, it can also act as a wave. And that means in quantum mechanics, we cannot actually use Newton's laws of motion as well as the law of conservation of energy to study and describe the behavior of our system, the behavior of our electron. And in quantum mechanics, the Schrodinger equation replaces Newton's laws of motion. So in quantum mechanics, Schrodinger's equation takes the role of describing and predicting the behavior of our systems, the behavior of our electron. So, now, Schrodinger equation is basically a differential equation that allows us to determine an important quantity in quantum mechanics known as the wave function that basically describes how our particle or our electron changes with respect to time. Now, we'll discuss what the wave function is in just a moment. First, let's look at the following equation. So there are two main forms of Schrodinger's equation. So we have the time-dependent and the time-independent form. This is the one-dimensional, non-relativistic time-independent equation. So the one-dimensional part means that our object, our system, in this case, let's say the electron, is traveling along a single dimension, in this case, along the x-axis. The time-independent part means that the wave function does not depend on time, it only depends on our position. And in this equation, the wave function is given by psi with respect to x, because the wave function psi depends on x, the spatial position of our object electron along some horizontal one-dimensional axis. Now, basically, this differential equation was invented by Erwin Schrödinger in order to describe the matter wave that is produced by our electron, by our objects, which are down on the subatomic and atomic levels. In particular, the above equation describes a single free particle electron moving along a single dimension, let's suppose, along the x-axis. So the free particle simply means our electron does not actually feel any form of force. So that implies that the energy and the momentum of our particle, our electron, remains constant. So, as we just mentioned, in quantum mechanics, because of the wave-particle duality of nature, we cannot use Newton's laws of motion to describe the behavior and predict the behavior of our systems. Instead, we have to use Schrödinger's equation. And Schrödinger's equation itself basically allows us to determine something known as the wave function. But what exactly is the wave function? Now, in quantum mechanics, we use the wave function, which is basically a quantity, and we use it to describe the displacement or amplitude of our matter wave that is produced by that particle, in our case, our electron. Now, by taking the square of the absolute value of the wave function, we can also determine the probability of finding the particle at some given moment in time. So the wave function is basically what describes how our system on the atomic and subatomic level behaves. The wave function describes the behavior of our electrons. Now, unlike in classical mechanics, which basically uses a deterministic theory, quantum mechanics uses a statistical theory. It uses a statistical approach. So basically, we cannot actually predict the exact location of an electron, but rather we can use probability to predict where our electron might be found with some high probability. And this is exactly what the wave function allows us to do. So we can basically conclude that in quantum mechanics, Schrödinger's equation replaces Newton's laws of motion, and we use Schrödinger's equation to basically determine what the wave function is. And then we basically use that wave function to determine the behavior of our subatomic system, for example, our electron. And this entire idea comes from wave-particle duality of nature. The fact that on the atomic or subatomic level, our electron or any other particle doesn't only act as a particle, but it can also act as a wave. As we discussed previously, the Schrödinger equation is basically the analog of the second law of motion in quantum mechanics. So in the same exact way that we use the second law of motion in classical mechanics to describe the way that our object moves and behaves, in quantum mechanics, the Schrödinger equation takes the role of helping us describe describe the motion and behavior of our system on the atomic and subatomic level, and it uses something known as the wave function given by the Greek symbol psi. So basically, the Schrödinger equation is a differential equation that expresses itself in terms of the wave function, as we'll see in just a moment. But first, let's actually try to understand the role that wave function takes in quantum mechanics. So what exactly does the wave function do in quantum mechanics? So let's go back for just a moment to classical mechanics. In classical mechanics, if we have an object moving, let's suppose, along the x-axis in one dimension, to completely describe the motion of that object, all we need to do is calculate two quantities. So if we know precisely what the position is of that object along that x-axis, and we know what the momentum is of that object at the same instant in time, then we can use these two quantities to basically determine what the motion of that object will be at some future moment in time. So in classical mechanics, position and momentum is needed to sufficiently describe the motion of our object. Now, in quantum mechanics, things aren't so simple. In quantum mechanics, we have the wave-particle duality of nature, and according to Heisenberg's uncertainty principle, we cannot precisely know the position of that object as well as the momentum of that object at the same moment in time. So that means in quantum mechanics, we cannot actually use these quantities to describe the motion of that object, and these quantities are basically replaced by quantities we call the wave function given by the Greek symbol psi. So, in quantum mechanics, the wave function describes the motion and behavior of that object in a similar way, in an analogous way, that position, momentum, describe the motion of that object in classical mechanics. So let's suppose we have a certain particle, let's suppose an electron with a mass m that is moving in a positive direction along the x-axis. Now, at any given moment in time and point in space, the behavior and the motion of our particle, our electron, is completely given by the wave function. So psi depends on two variables. So the wave function depends not only on the position along the x-axis, but also on the time. So the wave function is itself a function of two different variables. Now, what exactly does the wave function look like on a two-dimensional page, on the two-dimensional board? So in the same exact analogous way that the position and momentum in classical mechanics can take any real value, for example, it could be 1 or a million or any number in between, the wave function could take the